All right, so yesterday we talked a lot about acid chlorides, and we said we can interconvert a carboxylic acid to an acid chloride by using thionyl chloride, same reagent we used for alcohols. The mechanism, though, we said was a bit more complicated, so we worked through that mechanism. But same idea, we generate sulfur dioxide gas, which is the driving force of this reaction. Acid halides are really nice because they're the most reactive of the carboxylic acid derivatives. So we can have it react with water to go back to a carboxylic acid. We can have it react with an alcohol to make an ester. We can have it react with amines to give amides. And then last but not least, we finished up talking about reduction, where we can have a hydride attack in and get us all the way to a primary alcohol. One thing that we did notice, though, is that it is too hard to stop here. All right, so this gets a little bit tricky because chemists might have a situation where they want to stop at the aldehyde. So if we want to stop at the aldehyde, we can't use lithium aluminum hydride and we can't use sodium borohydride because we will accidentally over-reduce it, right? Because even sodium borohydride will reduce the aldehyde. So let's take a look at a new reagent focusing on stopping at the aldehyde. All right, does anybody have an idea on what we could do to potentially slow this reaction down? Hinder it, right? So bulk it up. If our hydride source is really, really, really bulky, maybe that'll slow it down, make it a less aggressive reducing agent. So that's exactly what they did, was they tried to explore various reducing agents that were bulky. So use a bulky reducing agent. All right. So after a considerable amount of research, they settled on this one. So it kind of looks a little bit crazy, and then the countercation is lithium. But you can tell it's got these tert-butoxy arms coming off of the aluminum that are huge, right? So it's kind of like this monstrosity of a reducing agent with one little hydride that it can deliver. So it's really going to slow it down. So let's take a look at how we name this. So this is named lithium tri tert-butoxy aluminum hydride. Or, if that's simply too much for you to write out, you can write LiAlOTBU 3H. Or, what you often see in our textbook is it condensed even further, where they just say LiAlOR3H. And really, it's indicating that this R group is equal to some sort of tert-butyl group. I don't know why they condense it down so much in our book, but we should be aware that that R group stands for a tert-butyl group in our textbook. Does that make sense? So this one's so bulky that it will only react with acid halides. All right, so let's try this out. I'm going to give you a problem and see if you can figure out how to work around it. So this would be a synthetic challenge. same as my notes. All right, and there might be more than one way to do this. Let's try working backwards. We've seen a couple different ways to make aldehydes so far. The one we just covered was from what? Acid halides, so maybe that's one route. Like I said, I really like working backwards because sometimes it can be overwhelming working forwards. So we can say, well, maybe this was an acid halide, and maybe we used LiAlOTBu3H. So maybe that was all that was needed. And then we could say, all right, we can go from here to here pretty easily by using what? SOCl2. All right. Or what's another way of making an aldehyde? PCC, right? So we could make an aldehyde using PCC. Let me slide this over. But that would have required this to be an alcohol before. How can we go from the carboxylic acid to the alcohol? So if we use LAH, we'd reduce the ketone too. We could use a protecting group, but there's an even faster way than using a protecting group. Not quite. Sodium borohydride wouldn't reduce the alcohol. Not quite. It's another reagent. It was a newer reagent that only reduces carboxylic acids, won't reduce other functional groups. See if you can find it in your notes. Yes, BH3THF. So do you remember me talking about that the other day where I said this is selective? Somebody else said, well, why don't we just protect the ketone and then reduce it? This trims it down to one step, right? So as a chemist, I would prefer to do one step over many steps. So both of these routes could work. Why might we choose the blue route over the green route? Yeah, PCC is toxic, right? We don't want to use chromium if we can avoid it. So maybe this is a good workaround. Not a perfect workaround though. Has a super low atom economy. That lithium tributoxyaluminum hydride is not the most atom economical reagent we could use. And then thionyl chloride is nasty stuff to work with. It is not easy to use. So neither one's perfect, but we're able to plan out multiple attacks for making this one molecule. Make sense? All right. Now let's look at the next class of reactions. These are reactions with carbon-based nucleophiles. All right, so we already talked about Grannard reagents briefly. And we actually did this while we were working through our practice problems at the start of class. So we said if we use methyl magnesium bromide, that we will make an intermediate ketone, right? So I'm not even going to bother with the arrow pushing. However, it's too hard to stop here. The Grannard reagents that are floating around will react with this almost as quickly as they would an acid halide. So the reality is any excess reagent that would be made, and once it's finally quenched with water, would look something like this, where we have a tertiary alcohol. Like I said before, it's equivalent to the reaction we saw with esters, where it just adds in uncontrollably, right? So we could do this, however, there might not be a reason to necessarily use a Grannard reagent in this situation. It'd be a lot easier to start with an ester. Esters are a lot easier reagents to handle and to work with. So this could work. However, it would look kind of odd if this was your target. All right. However, like we saw previously, chemists don't like being told, no, you can't do something. So they tried to develop a way at stopping at the ketone. This is called the Gilman reagent. And these are organocuprates. So this is getting into organometallic chemistry again. And the Gilman reagent's kind of unique. So if you have an acid halide, a Gilman reagent has two R groups, meaning two alkyl groups bound to copper, and then lithium's also coordinated with copper too. So in this case, the R group acts as the nucleophile. And when we react these, we can actually stop directly at a ketone. And this is due to a couple different things. What do you think the big thing is that's allowing it to stop at the ketone? Yeah, so copper is behaving like a different metal, right? What else? It's super bulky, right? Because it's bulkier, it's going to slow down the reaction kinetics enough where it actually won't react with the ketone once it's formed. However, it will react with the acid halide. All right? I want to show you a side thing too. I've seen this a lot on synthesis problems lately and last term, where I see students that'll have a reaction like this and they'll say, hey, why don't I just do this and do an SN2 reaction? Grannard reactions are really, really terrible at doing SN2 reactions. It just leads to a mess of products. It's not a good way of forming a new carbon-carbon bond to an alkane, right? All right. However, if we use the Gilman reagent, we can actually do SN2 chemistry with it. So Gilman reagents allow for SN2 reactions. Does that make sense? So it's one of those things, you may have seen comments on your exams where I said, don't do this, don't use the Grannard reagent to try to do SN2 chemistry. This is a novel workaround that you can now use though. All right, so that's pretty much it for the acid halides. What I like to do at the end is make a mini reaction map. So you remember reaction maps from last term? We're just gonna make a mini one for acid halides. All right, so how can I go from a carboxylic acid to an acid halide again? Sockle, right? All right, and then how would I go backwards? We could use NaOH or just water in this case. We don't even need a super strong nucleophile. So water would work well here. Normally, though, we want to ensure that we have this final proton off the very end. So oftentimes you'll see water and some sort of acid source. So really just dilute acid will accomplish this to ensure that it's protonated at the end. All right, so that's pretty cool. Then we can think about our functional groups that we can make from acid halides. So now we're kind of focusing in on that center part. We just saw that we can make ketones. So we can make a ketone using the Gilman reagent. So in this case, I'll just say R2CuLi, where we've added in an R group on there, right? So we can make a ketone now pretty effectively. All right, and then we saw also that we could make tertiary alcohols. How do we do that? Grannard reagent, right? So RMgX in excess, followed by water, would allow us to form that tertiary alcohol. All right. Let's consider this. How do we make an aldehyde? Can't just throw in lithium aluminum hydride. We said that'll blow past the aldehyde and go to the alcohol. That was the bulky one that we just learned. Right? So that was our super bulky hydride source, right? We said that allowed us to stop at the aldehyde without reducing the aldehyde that we've created, right? If we use other reducing agents, we would just go right past that aldehyde to an alcohol. So we have to use a super bulky one. All right? Along those lines, we can go to a primary alcohol. Yeah?
Doesn't the 3 have to be outside?
Oops, sorry, you're entirely right. OR3H, perfect. If we want to go to a primary alcohol, we can purposely overshoot it with LAH because we're just trying to get to the alcohol, followed by water. So that's pretty good. All right, let's say I want to make this amide. What should I use? Yeah, would we use a primary, secondary, tertiary amine? What sort of amine would we need? Primary amine. So, and we would use it in excess because we need it to act as its own base. We could also do this with other amines too. So maybe we use HNR2. In excess, or maybe we do this with NH3 in excess. All of these give amides though, right? So that's pretty useful. And then last but not least, we've got one more. How can we make an ester? Yeah, with an alcohol, so ROH, and then typically pyridine as well. So you can see this one reagent is super duper versatile. It's an incredible building block that we can use to make a wide variety of functional groups. And then once we have an ester, alcohol, aldehyde, whatever we've made, we can derivatize it further from there. So this, in my opinion, is the most important reaction map from the chapter. It's also, in my opinion, the biggest reaction map from the chapter. So if you can master this reaction map, you'll be in pretty good shape. But just try to make sure you remember all of the reagents because it is confusing and we've learned a handful of new ones we haven't seen before. All right. Now let's go into the next most reactive species. Does anybody remember what's next most reactive after acid halides? What's that? Anhydrides. So if we go down the list, anhydrides were next. So we'll look at preparation. Good thing is we already did most of the legwork with acid halides, so there's not going to be a whole lot new here. And like I said before, acid halides are super versatile. So there's one we didn't even cover yet, but we can use. I'm going to put this as R prime. What do you think we should put in that box? Check with your neighbor and see if you have an idea? If we think about it, right, we're just adding in this chunk. So we know that the oxygen here is going to be the thing forming the new bond to that carbon. Should it be positive, negative, neutral? What should that oxygen be if we want it to be a decent nucleophile? Negative, exactly. So for this one, we can use a negative charge and then just do nucleophilic acyl substitution. What do we call this sort of functional group? It's not a carboxylic acid because it's deprotonated. Carboxylate. So this would be a carboxylate salt. We can react this with acid chlorides to make an anhydride. So this is one method that's pretty easy to do. We don't even need to do the mechanism because we're pretty familiar with it attacking in and then kicking off chlorine. So we'll just kind of leave it at that. So that's one easy method. For simple symmetric anhydrides, there's another method. And this is used to make a lot of commercial anhydrides, meaning reagents. All right, so you can actually just take a carboxylic acid and heat the snot out of it, and it will actually couple together. Do you think this is something that people do in labs? No. Heating something to 800 degrees is a challenge, right? So you have to do this in special reactors in an industrial facility. This is something you would never see in a synthetic reaction. Beyond just the logistical hurdles of getting the equipment, what's the other downside of this reaction? If, let's say we were wanting to do this in a natural product, what's the problem? We would burn our product, right? It would turn into charcoal at 800 degrees. So really this only works for simple small molecule anhydrides. Anything with complicated functional groups would decompose very, very, very quickly. So they show this in the book, but I always like to throw in that caveat that it's not a good way of making more elaborate anhydrides. The method above is the much better method. All right. So let's take a look at this. Students often ask, well, why on earth would we use an anhydride if acid halides are such versatile intermediates? Anhydrides are sometimes kind of in the middle, so it's the Goldilocks effect where you want something that's just right. So anhydrides are sometimes better than acid halides. All right, so I'll show you an example. Anybody know what this stuff's called? Give you a hint. It's in zit cream. Salicylic acid. I remember being an awkward teenager and my mom yelling at me because all of our towels were bleached on accident from my stupid zit cream. That's salicylic acid. Salicylic acid can be treated with this anhydride. What's this anhydride called? Think about the carboxylic acid that was used to make it. So if we break this apart, what would that carboxylic acid be if it had a proton, right? Acetic acid. So this would be acetic anhydride. So you can react salicylic acid with acetic anhydride. And what do you think the product will look like? Will it react with the carboxylic acid? Probably not. However, the alcohol, definitely. Right? Because if we think about it, right, this whole group lost as a leaving group, which meant that this was the group that we added on right there. So we've added on this acyl group. So these are called acylating reagents. In this case, they react really well with alcohols. If we were to use an acid halide, we might accidentally make an anhydride at the top too. Yep. Why doesn't the whole thing add in? Yeah, so let's take a look at this, right? So I'm going to cheat and not show all the intermediates. But this oxygen would attack in, agreed? Kick up electrons to the oxygen, we make a tetrahedral intermediate. I'm not going to bother showing that, but then in the next step, we kick this off as a leaving group, right? So that whole green chunk falls off as a leaving group in this reaction, leaving that orange acyl group directly attached. All right, so you might be wondering, okay, cool, we can get an acyl group. Oftentimes, if you remember way back to first term, these are abbreviated as AC, just because they're easier to abbreviate that way. Does anybody know what this is on the right-hand side, though? Well, of course, it's acetyl salicylic acid. Ugh. I take acetyl salicylic acid when I have headaches. It's called aspirin. So we can take zit cream and turn it into aspirin if we really want to. Kind of cool. I wouldn't trust my zit cream being turned into aspirin, but I guess if you're brave. All right, let's take another one. I think this might even be a better example. What would this starting material be called? So what's the parent? Orphenol. In this case, it'd be para-aminophenol. So that would be the parent for this one. It's always hard to know which parent takes priority over the other one. I'm not concerned with you knowing that. All right, now what we're going to do is we're going to react this again with acetic anhydride. My question for you is which side will be acylated first, the oxygen side or the nitrogen side? Which one's the better nucleophile? This is tricky, right? Both of them have lone pairs. But which lone pairs are going to be more available for a nucleophilic attack? Let me phrase it a different way. Which one's holding on to its lone pairs less tightly? Nitrogen, right? So nitrogen is a better nucleophile than oxygen. So in this case, when we do this reaction, just like we saw before, we can do a nucleophilic acyl substitution where this chunk gets added on as our acyl group, this whole chunk gets lost as our leaving group, and we get to our final product. Another cool thing is this is Tylenol. So this is how they prepare Tylenol. Does anybody know the downside of taking Tylenol? I think we talked about it earlier. If they presented Tylenol to the FDA today, the FDA would laugh at it and say, you're going to kill people with this. This will never be FDA approved. The reality is it's been around so long, it's been grandfathered in. It's kind of weird to think about that way. The problem with Tylenol is it has high liver toxicity, which means the difference between the effective dose and an overdose in many cases is a pill or two. So if you have kids and you give them Tylenol, do not give them adult Tylenol. Make sure you give them children's Tylenol and that you choose the appropriate dosage. Don't say, well, they're really sick, I'll give them a few pills more. You could end up destroying their liver. So it is kind of this weird FDA thing. But there are some drugs that just stuck around because consumers would freak out if we took Tylenol off the shelves. There's a few drugs that got grandfathered in. The other one that blows my mind is Pepto-Bismol. How many other drugs do you find bismuth in, right? Bismuth is some nasty stuff, but it appears to be relatively safe in Pepto-Bismol. Yeah. Yeah.
So in the previous reaction, we added the acetone to the alcohol. Would we not also add on the alcohol in the second?
Yeah, so that's a big question. If we kept on pushing this with extra anhydride for the bottom one, we could potentially acylate the alcohol, but if we control it, meaning use the correct stoichiometry of reagents, 1-to-1 ratio, then it'll stop after it's done with the nitrogen, right? So this is one where we would want to control the ratio of reagents carefully. All right, so let's just finish up today, I think, with our map for acid anhydrides. A lot of this will look pretty dang similar. All right. So we've got our carboxylic acid off to one side. I'll put my anhydride in the center. How can we go ahead and make this anhydride? We kind of briefly talked about that. Yeah, first we need to make it into a carboxylate, meaning get rid of the proton off of this carboxylic acid. We want that to have a negative charge so it acts as a good nucleophile. So how could we get rid of that proton? Yeah, NaOH, cheap base. And then 2 would be to have it react with our acid halide, right? We just covered how to make that, so we can couple that to our acid halide and make an anhydride pretty easily. All right, conversely, how do you think we can reverse this? What's that? Water, just like with acid halides. So we can use water, and typically dilute acid will accomplish this. Again, like I said with acid halides, they're used in tear gases because they're lacrimators. They'll make your mucous membranes kind of feel irritated. Anhydrides do the same thing. They'll react with the water in your eyes and in your lungs. All right, next question though. What do you think would happen with a Gilman reagent based on what we saw previously? Yeah, we can make a ketone. So really, anhydrides are I'm going to make this R prime, are remarkably similar to acid halides in terms of their reactivity. They're just a little bit more gentle, right? So they do a lot of the exact same chemistry. All right. Next one. So Grannard reagent followed by water. What do you think we'll get out here? So think back to the acid halide chapter, right? Grannard reagents add in uncontrollably. Same thing here. If it adds in uncontrollably, we'll get 2 alkyl groups installed and we'll get a tertiary alcohol out. So exact same chemistry that we saw in the previous chapter, which is kind of nice. Yep, because if we think about it, right, this whole chunk would act as a leaving group. So once one of these adds in, we'd make a ketone. Can't stop at the ketone, so it'd add in again and get us all the way to that tertiary alcohol. All right? In fact, I'll leave the circle just so we remember that 1/2 is falling off as a leaving group. All right, let's think about this one. What do you think will happen here? Ketone or aldehyde, right? Because hydride's adding in here. Oftentimes, these reagents have different R groups. Like I said, the ones with the tert-butyl group will react exclusively with acid halides. However, if you vary the R group, sometimes these will work with anhydrides. It's not super common to do this reduction though. All right, next one. How can we make an ester? We could use an alcohol, right? And pyridine typically to soak up any of the base. And I won't show all of the amides, I'll just pick on one. What would we need to make an amide? NH3 and excess. All right, here's kind of the limitation though, because I'm going to put an asterisk here that this is super slow. This isn't as easy as with an acid halide. Therefore, most chemists would never use an anhydride to make an amide. The reaction rates are just super sluggish and not very easy to work with. So it'd be much faster to use a different reagent. Does that make sense? All right, I think that's where we're gonna stop today. Tomorrow when we come in, we'll jump into the next most reactive one. What's the next most reactive one? We've done halides, so acid halides. We've done anhydrides. What's next? An ester. So we'll get into esters tomorrow, and then we'll do amides and nitriles to round up the chapter.